this working? It's working. Hi. So, I am recording this lecture. The goal of this week is to review the material that's on the exam this Friday. So the exam will be Friday during our recitation. Our recitation's at 12 in the other room. We'll probably start around 12:15 to give the late people some time to get here. You have your project due in a week. So I'm hoping that most people are basically done, at least with the coding, and now they're typing the report. You know, spend that time getting that done, but also I pushed it back to Monday so that you can focus on the exam, because I want you to do well in the exam and not over stress about the project due the same week. And additionally, your last homework is due on Wednesday. I have posted practice quizzes for all of the material, so you can go take those practice quizzes as many times as you want. Today and on Wednesday, the plan is to go through all the note sets that we have on the exam and also do the exam from last semester. That's the itinerary for this week. And cover any extra problems if we have time that you want to go over. I have some problems that I want to cover today from the quiz to kind of continue to stress certain points, and then we'll go from there. Any questions about things logistically? So I'm going to try to go through this not super fast, but I'm going to go through and try to highlight the things that I find most important and the things that give students the most struggle. And we'll start with note set 18, which is on nonlinear regression. And just like linear regression, the big thing is the sum of the residual squared. So the residual, if you remember, if I were to draw a graph, I might have a bunch of data points, and I want to fit some sort of curve to those data points depending on the function. And keep in mind that yi are the data points and the function itself, maybe I'll do in blue. If I were to draw some function that goes through the data points, maybe something like this, the residual, by definition, is the distance between the y value and the function value. So if I were to look at the distance between the y value in red and the function value in blue at that same x location, that will give me the residual. This is the residual, which we called E sub I. This is the residual. And what is the goal of regression in general? Somebody want to volunteer? Carm.
Isn't it just to keep all the data points as close as possible?
Right, they're trying to keep the data points as close as possible to the function. More mathematically speaking, in regards to this, what are we trying to do?
Oh, just me.
Yeah, we want to minimize this. Our goal is to minimize this because, again, this whole thing here is the distance between the points. And the curve of best fit. And I'm saying curve because this is nonlinear regression. It's not a line. It could be a quadratic or an exponential or something weird. We want to minimize that distance. So to minimize that distance, we take the partial derivative of this SR variable of this thing with respect to the coefficients we were trying to determine. That is what we did for linear regression, and the same concept holds true for nonlinear regression. It's the same exact situation. And I give you some general names of things here. You do not need to worry about these names. I'm not going to have you memorize, saturation growth formula or anything like that. But again, this is kind of illustrating what I just drew we see that the residual is the difference between the red dot and the blue function, which again is our model and our estimate. Why do we square the residuals again? Yeah, to avoid canceling them out, because you see in this picture that if you look at this point and this point, the left one is above the blue graph, the right one is below, which means that if you don't square the distances, you risk canceling them, which might make you think you have a smaller SR than you actually do, and make you think you have a better fit. That makes sense. Doubts about that? Okay. So in this note set specifically, we looked at an exponential type of fit, where our two unknown variables are the amplitude of that exponential, which is A, and then also the exponent term B. And we see we have an exponential relationship between the output of the function and the input of the function, x of I. And we went through two different ways of doing this. One way, where we did the least squares method, where we took our y values and subtracted ae to the bx, took the partial derivatives with respect to a and b, and then you ended up with the system of equations. What was the problem with this method? Yeah, it's really difficult. Why was it difficult? What did we end up needing to do to determine our values, Jacob? Yeah, we had to do some sort of root finding technique, some other computational method, which gets to be pretty difficult. I am not going to be testing you on this because of how difficult it is. Yes. No, least squares method's totally fair game. Yeah, I won't have you find the roots, is essentially what I'm saying, because that makes the problem a lot harder, right? So there's no root finding. But just to kind of illustrate again this idea of the least squares method, we take our data points and subtract our best fit function. And in this case, the best fit function was this exponential ae to the bx. And remember, on the second exam, I gave you some f of x. This equation is always yi minus f of xi inside of here. So depending on the situation, you might have a different f of xi. You can't just assume it's going to be this. That's what a lot of people did on the second exam, where I gave you that f of x was a naught. And a lot of people are like, oh, I'm going to plug in a1x plus a naught, or whatever they plugged in. Yes. That was on the second exam. So the question was basically saying, find the coefficient of a naught to minimize the sum of the residuals squared, given that f of x was a naught. So your summation should have been yi minus f of xi squared, which should have been yi minus a naught squared. That's the correct way of doing it, because I told you what f of x was. But what a lot of people did is they did yi minus a1xi plus a naught, which shows me the concepts weren't really grasped. It was just more of a, I memorized something, let me just use what I memorized. That's not okay. I need you to understand what's happening here. Again, we're finding the difference between these data points and the chosen function, which could be anything. In that second exam problem, I told you it was a naught. In this exam, it could be something like an exponential or a quadratic or whatever. And we've seen that in our homework recently, the most recent homework you had, not the one due this week, but the one that was due last week, where you had nonlinear regression with like a spring. I think the problem was like kxi squared or something. That was a least squares method, where I gave you the function we were trying to fit. Is that clear? Any doubts about that? Yeah, that was on the exam. That's correct. That's not for this note set. That was from the past. Well, the f of x equation was just a naught for that specific example, right? So we do subtract the whole f of x. It just depends on what f of x is. So again, this thing in black was on the last exam. I'm going to erase that because it's not relevant to this exam, but just be careful about what you're doing. So with this whole nonlinear regression, we took partial derivatives with respect to A and with respect to B, and it got really messy and ugly. We're not going to focus on that. We did some examples, so do bisection method. And then we ended up with this nice curve here where we see that our arbitrary AE to the BXI with the found coefficients of A and B, we are able to get a graph that goes through the points fairly well. That makes sense. So the other thing that was a little bit more important because it's easier is this idea of doing nonlinear regression with transformations, where what is the objective of this? Yeah, to turn it into a linear fit instead of an exponential fit or something more complicated. You saw some extra examples in your homework where you had some weird fit. You had to convert it to a linear one. What is the benefit of the linear fit? Easy to solve. Why? Yeah, we have the equations for a linear regression model from the previous note sets. If you go back to note set 17, for example, you'll see that we have equations for A1 and A naught for a linear fit, or just A1 for the fit A1x. So if we get this into a linear form, we can use those equations and leverage them, which is super convenient and super easy. So we could see in this example, I took the natural log of both sides to convert our exponential equation to a linear one. Because if you take the ln of both sides, the beauty is that you can separate these two. That's the property of natural logs. Natural log of xy is natural log of x plus the natural log of y. And once you do that, natural log of e to the bx, that bx can come down. Then you have the natural log of e, which is just 1. And you end up with this type of equation here. ln y is ln a plus bx, which does not look like a linear equation at the moment. We have to go ahead and substitute in some variables. So what we did here was we said, okay, let ln y be z. Let ln a be a naught. Why do you think I call that a naught and not a1? It's not connected with the x. That's exactly right. Because our equation that we want to do linear regression on is a naught plus a1x. We want the x to be next to the a1. So now we can do this linear regression. So this is a linear regression between x and z. This makes sense. Any confusion? Okay. And here are the equations from the note set before, where instead of a z, we had a y. But because we've done this transformation, we're not using y anymore. We're now using z, because that's what makes the equation linear when we take the natural log and use that value instead. Confusion. Okay? Beautiful. So once you go through to find what A1 and A naught are, specifically based on this equation here, we have to convert back. So if you look to see what I did at the top, we said that A naught was the natural log of A. Because at the end of the day, what we're trying to do is find the fit A e to the bx. So A naught is the natural log of A. and b is strictly equal to a1. So we have to go ahead and do some exponential to figure out what those values are. Specifically, well, that is wrong the way that I wrote it. It should be e to the a naught, not e naught to the a. That makes sense, though? That's the general idea. We're backing back out those values, those definitions. So we do an example here where we see the main thing we had to do was take the natural log of the y values. That was the big thing here. Because we're not regressing between x and y anymore. We're regressing between x and z. And z, based on how we wrote it, is the natural log of all those data points. So here in this example, we see that y is 2.7. If we take the natural log of that number, that will give us the z for that data point. And we'll do that for all of the y values. And what's nice is that once you do this, you can use our simple linear regression equations, quote unquote simple. They are simple compared to the other stuff, but it's still a little messy. Once you do that, you can go ahead and find out what your A1 and A0 are for your specific linear regression model between X and Z. And then we have to convert back using the exponential, because remember we substituted in, like I just discussed. Questions? I know I went through that kind of quickly. I can go through it slowly if you'd like, but go ahead and give me some feedback on how we're feeling. Thumbs ups from people. Thumbs ups? Yeah. Beautiful. Okay. Markley, you okay? I didn't see your thumb up. I saw it maybe down here. That's got thumbs down. Okay. So we can see that if we transform or do or not do a transform, we end up with very similar graphs, but that's not always the case. We'll see that our transformation will not be as accurate in some cases as the more difficult technique. And nowadays, most people will just do the non-transformed way because it's a lot easy. It's pretty easy to code that in MATLAB if you're decent at coding. But if you're doing it on paper, then transforming is obviously a lot simpler. Doubts about note set 18. I think that's the whole note set. I have the code here. You won't need the code on the exam. I might ask you for like what a certain line of code does, or I might ask you to write a line of code, like something like polyfit, for example. You know, things like that, which we'll talk about soon. That type of stuff is fair game for Hensley. No, not necessarily. You could transform anything. Like in your homework, you had other types of transformations that were, you know, weird things from your last homework. The one that was due last week. I forgot what the problems were like, but you might have seen something that was like y is equal to, what was like 1 over ax plus b or something like that. I don't remember what it was, but to transform this, you have to take the reciprocal of both sides. I think it was actually something like this. So to transform that to a linear equation, we want our ax plus b or something like it in the numerator, because that is linear, right? So if I were to flip both sides, I get 1 over y is equal to ax plus b squared. Then I'll take the square root of both sides. Okay. And this will be what I call z. Now I'm regressing between z and x. But I have the given data. I have x and y data. What I would have to do is take the literal y values, take the reciprocal of them, and then the square root. Does that make sense? So that's a transformation. All these transformations have the same idea, where we're taking a complicated equation and turning it into a linear one. That makes sense. Cool. Our next nonlinear regression problem was on polynomials. And by definition, because I think some people were confused about the quiz problem and stuff, a polynomial, let's say fn of x, this is going to be a polynomial. This would be something like a0 plus a1x plus a2x squared plus dot 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 an x to the n. You do not see any sinusoids in there. You do not see any exponentials. You do not see any natural logs. If those things pop up, that automatically makes it not a polynomial, meaning natural log of x. You can have natural log of a number. That's just a constant. But if I have the natural log of x plus 4 ln x, x to the 6th or something, that's not a polynomial because it's the natural log of x screwing it up. I'm just reminding you of that since that was a question people had with Gauss quadrature. What's a polynomial? When is it exact? And so on. So in this note set specifically, what we're trying to do is regress to some sort of quadratic or some sort of cubic function if we have that type of behavior. And the procedure for this is identical. We have our function f of x. We'll define the residual. Remember, our residual is yi minus f of xi. Oops. So if our function was a quadratic, this might be something like yi minus a naught plus a1x plus a2x squared. Right? This is the residual. I have my fit, my quadratic fit. I'm looking for the distances between the data points and that fit. And then we'll go ahead and want to minimize the sum of this, well, the sum of the squares of this. We haven't written that out yet. By doing what? What do I do? So if you have, let's scroll down. Here is our regression model. F of x is a naught plus a1x plus a2x squared. This guy. Our residual is defined as y sub I minus that function. So y sub I minus that function is here. That gives us this as our residual. What we want to do is minimize the sum of the squares of the residuals, where we'll plug in that subtraction into this equation. We're summing them up for every data point. And now we want to minimize the sum of that, but we do not know what a0, a1, and a2 are. So how do we go about and minimize it? Markley. You will take partial derivatives with respect to a0, a1, and a2, the unknown variables, right? So we can see I do this first with respect to a0. Maybe we'll actually do this. So we have dsr, the a0. With series, I can go ahead and take the derivative of the term inside of the summation. I don't need to carry out all this math. I can just take the derivative right away. If I'm taking the derivative of this whole function and I'm squaring it, what I need to do is the chain rule. I'll pull down the 2 from the exponent. The exponent goes to 1, right? Yeah. Then what? Yeah, I have to multiply by the partial derivative of that inner term with respect to a0. What's the partial derivative of this with respect to a0? -1. Do we see that? So if we go through that math, you can see here that I brought down the exponent of a 2, and then I multiplied by the derivative of the inside with respect to a0. That's -1. Okay? So if you go through some algebra here, we can note that this 2 and this -1 can cancel because it's equal to 0. I can rewrite this as the summation of yi minus the summation of a0 minus the summation of a1xi minus the summation of a2 xi squared, and that's equal to 0. Yeah. That's what I just said. So divide by the 2 and the -1 because we're equal to 0 on the right side. You see, I could take this 2 out of the summation. I can also take this -1 out of the summation. And now I have a number times something is equal to 0. That number can go away. Doesn't matter. So we can go ahead and try to bring all of our unknowns to one side, which is the A0, the A1, and the A2. This will give us a summation of A0 plus the summation of A1 xi plus the summation of A2 xi squared is equal to the summation of yi. Do we see that? Okay, summation of A0. What is that? Remember, A0's a constant. It does not depend on the series. So A0 can come out. Then I have the summation of 1. What's the summation of 1? N. Remember, this series goes from I equals 1 to n. If I do A0, the summation of 1, this thing is the same as 1 plus all the 1s, n times. Is that okay? Okay. Plus, the A1 can come out of the summation. This will be A1, the summation of xi. Why can't I take the x out? Yeah, it has an I. It depends on the index of the summation. I can't take that out because depending on what I is, it changes. Plus, same deal over here, A2, the summation of xi squared. That's the summation of yi. Is that okay? So I still have 3 unknowns. I can't really do much with it. What did I do next? Take another partial with respect to A1. And then we'll take another partial with respect to A2. That'll give us 3 equations and 3 unknowns. This is all the math I just did. You end up with this equation here. And then I do this with respect to every one of the variables, 3 equations, 3 unknowns. Here are the 3 equations. Of course, they're on separate pages. I'll just look at these guys. What we see is that we have a constant times some numbers. Right? The summation of xi, even though it looks complicated, is just the sum of a bunch of x values. That is a number. The x values might be 1, 2, and 4. Add them together. It's a number. So this is a number multiplied by A0. This is a number multiplied by A1. This is a number multiplied by A2. And we'll see that for all 3 equations. So what did we do? 3 equations, 3 unknowns. How do we set that up? In a matrix, that's correct. So if you put it into a matrix, it looks something like this. Which again, it looks kind of complicated, but it's really not that difficult to derive if you practice it. And another thing that's useful is that there's actually a nice little pattern that emerges, is that if you look from left to right, we see that the exponent of xi gets bigger with each element. So this first one is xi to the 0, basically. It doesn't exist. And you have xi to the 1, xi2. You see the other part of the pattern? It's the same thing going down. Choose your favorite row or column. You'll see that pattern emerge, which is super nice and convenient in case you get stuck. You see that this is 1, 2, 3, 2, 3, 4. I'm just picking arbitrary things. 2, 3, 4. There's this nice little pattern that's emerging. Do we see that? Okay. Similarly, on the right side, if you were to look going down, it's the same exact thing. We have no x's, we have 1x, we have 2x. We have a pattern, except this time it's multiplied by y. That's just the result of the partial derivatives. That's all that ends up happening. Do we see that? Any confusion about that at all? Yes. Yeah, exactly. You just continue the pattern in both directions. Because if you have 4 unknowns, you need a 4x4. You need another column. You need another row. The pattern's still true. Right. Based on the proof we just did, where we took the partial derivative with respect to A naught, that will go ahead and establish that first row, and then the pattern just kind of goes from there. That makes sense? Yep. Cool. So then, of course, once you have this matrix, you can do things from the past, LU decomposition, Gaussian elimination. Not that I'm going to have you do that on the exam, but knowing that stuff is important. How would you actually solve it? Those types of methods. So I do an example here, where I give you some points X and Y. And if you note, because of the symmetry of the matrix, let's come back up actually and we'll look at it. What we can see is that this is squared, this is squared, that's squared. Those three are all squared. This is cubed, and this is xi to the 1 and xi to the 1. You see that it's symmetric? It's symmetric about the diagonal. So if I were to draw a diagonal here, we see that the points reflect over. It's symmetric about that diagonal. The reason I mention that is because at the end of the day, what that means is that you only need to find 5 terms. And the summation of xi squared, xi cubed, xi to the 4th. Which is tedious, but it's not difficult. You just have to be careful. And I go through all this math here where I gave you this table of numbers. What's the value of n? 4. There's 4 data points. Summation of xi. We will add up these xi values. Summation of xi squared. We'll do 1 squared plus 1.5 squared plus 2 squared plus 2.5 squared. Sum them all up. Same deal with the cube, same deal with to the 4th. Is that okay? You can see I do this all here. Again, I encourage you to look through these note sets and practice them to make sure you understand all the steps of these processes. So you can determine what your A matrix is, your B matrix, and so on. And you can see in this example, I end up showing a quadratic fit that goes through the points. Questions? Okay. I gave an example in MATLAB. So what I did with this code, again, I'm not expecting you to write code, but I expect you to be able to know simple lines of code. I define the matrix A. I define the matrix B. What does A backslash B do? It solves the matrix equation. It tells me what A naught, A1, and A2 are. And then what does polyfit do? It doesn't graph it. It finds the coefficients of A naught, A1, and A2. So this is the long way of doing it using our math. MATLAB has this programmed already to do it on its own. So polyfit x, y, what's this 2 mean? Second order. The question on the last exam was tricky for the true and false. I said polyfit x, y, 3 will find the 3 coefficients of a quadratic. That's not correct. It finds the 3, it's a third order. It actually finds 4 coefficients of a third order equation. Yes.
So it could be used to find So it could be used to find third order, but not a second order.
No, this polyfit can be used to find anything, but that specific question was only for qubit, for third one.
But X, Y to the 3 will work for qubit,
That's the only thing it works for.
not even anything higher.
You could go higher if you want.
But there's just one maximum point, one maximum number for those other things.
Right. I think I know what you're saying.
And
Yeah.
then the maximum for number you can put in the third space in the, like, what is that, A2, A1, A0 for the polyfit?
Those are the answers. I've commented that out.
Like, oh, like what goes in each space or something?
This is just showing what the output
Yeah.
of polyfit
I'm
is.
just trying to understand polyfit here.
Yeah, I recommend also like messing around on MATLAB at home.
Well,
Right.
because I even because on the second exam, I overlooked it when I
Right.
went there.
Let's talk afterwards about this a little bit more because I want to keep going. Juan. Nice. Shh, so loud. Go ahead.
How would you ask this, like, particular problem? Just say, like, find the quadratic.
Yeah, I can basically say, here's some data points, find the quadratic fit. Which, unless I tell you to, you can just use the pattern. But if I tell you to prove it, I expect you to show me the least squares method, the partial derivatives and stuff. Yeah, I expect you to show me that if I ask you to. Prove it, absolutely, sure. Considering that a lot of people messed up that type of thing on the second exam, you can expect something like that on this exam. Maybe for this, maybe for an exponential, for whatever it is. I'm going to basically tell you to do some sort of least squares method proof. You have to know your stuff. Last time, not many people knew it. This time is your second chance to prove to me that you know. Least squares method. We're not going to focus on this optimum order thing, so let's keep going. Any doubts? Yeah, that's why, because it's not on the test.
The optimization is on the.
The optimum order is not on the test. I already wrote the exam. It's not on the test. Optimum order? Yeah, we can if you want. No, it's at 20. So this is not nonlinear regression. We're back to linear regression, but specifically we're looking at the adequacy of a fit. What does that mean? If it's adequate, what does that mean? How good it is. Yeah, how good it is. Yeah, there's 3 techniques we used, which are there. Okay, what are 3 techniques? Does it look good? Visual inspection. We look at the standard error. We're going to talk about this in a second. What's the third? The coefficient of determination. Those are the 3 things we check. We can check to determine if a fit is good or not. And if you have like 6 data points, this isn't really that useful. But if you had thousands of data points, you can go ahead and code those things, and that'll make it more appropriate. Yes. Not that I'm aware of. I don't know. Polyfit is literally polynomial fit. So you can specify any polynomial to any order. Exponential fit, they probably do. I just never used it. Yeah, I don't know. So, how good is our linear regression model is the question. So the first thing we do is visual inspection. You can see here between the good and the bad. If I gave you these 2, it's like, which one's better? This one. I don't know. This one is better. It goes through the points better. Duh. The problem, though, with this type of technique is that it is very subjective. Maybe somebody else is like, well, I disagree with you, Brett. That one on the right looks pretty good. Subjective. Again, you go to industry, you'll see a lot of dumb people at exam. So, just a heads up that this is subjective. So as engineers, we typically don't like subjective. This is why we don't like English classes, because everything's graded subjectively. We would rather have an objective, numerical type of answer, which is our first concept of the standard error. Or what we can do is look to see some metric of how far away the data points are from the fit. That isn't just SR, but something kind of similar. And the first thing we did was we reviewed standard deviation. So standard deviation, the idea again is that you have some spread about the mean. That's what standard deviation is. So in this example, I have grades for classes, this top one. I have 3 students that got a 50. Is the standard deviation low or high? I hear middle, I hear low, I heard high. All across the board. So let's review again what this topic means. Standard deviation is the spread about the mean. What's the mean of this one?
50.
Okay, do we have any of those data points spread out about 50? No. Oh, so the standard deviation is literally 0, or I said low, but it's 0 because there's no spread. Good job. So class B, same average. 0 plus 50 plus 100 divided by 3. It's the same exact average, but non-zero standard deviation because we actually have spread. Here's the mean. Oh, look, we have points spread far away from it. We have points that are spread far away from the mean. That gives us an actual value of standard deviation. And I gave you this equation. This is the standard deviation equation, not the standard error. This is the one you see in statistics, where we take our x value of our data point and subtract it from the mean. That is basically saying if I give you that same graph with the 50, the 100, and the 0, x bar is 50 all the time. What is xi going to be? Let's say x1. Remember, I changes. What is x1, do you think? 0. So we do 0 minus 50, square it, plus, what's x2? 50 minus 50, it's 0. We square it, plus, what's x3? 100 minus 50, square it, add those all together, divide by n minus 1. What was n? 3. And that will give us a standard deviation. Am I speaking too fast here? Is this okay? Okay. So let's just go ahead and I'll just do this real quick just to illustrate this. Because it's going to be 1 over n minus 1, the summation of xi minus 50 squared plus 50 minus 50 squared plus 100 minus 50 squared. So we add up all those values, divide by 3 minus 1. That gives us our standard deviation of the data set, which again we see is not 0. Just like the residuals, why do you think we square it? To get positive numbers, because think about it. This 0 is 50 away. This 100 is 50 away. If you didn't square it, they would cancel. So you have to square it to make it positive. Exactly the same thing we did for the residuals. We don't want things to cancel. We want them to be both considered when we're doing our analysis. Doubts? So we're summing up distances from the mean. Standard error is the same exact type of thing, except we're not summing distances from the mean. We're summing distances from the line, which is basically the square of the residuals, right? That's the same exact thing. The only difference is now is that we divide by n minus 2. Why do we do n minus 2 instead of n minus 1? Does anybody remember? Wyatt? Right, so we found the y-intercept and the slope, we found these two from our regression analysis. We basically used the data twice to get those values. Every time we use the data, you have to subtract 1 from this n in the bottom. So thinking back, oh, it's 1. Yeah, there might have been a question that was just A1x.
Yeah. 'Cause,
A naught, you're technically saying is 0, which is essentially using the data, which is weird because, but what we're basically doing is making that assumption that A naught is 0, but we are using the data in a sense to generate that. So for that specific equation, it's still a line, it'd still be n minus 2 because you are approximating the y-intercept. So why is this guy n minus 1? What did we use the data for? To find the mean, x bar. We use the data once. We do n minus 1. Questions about that? Markley? Randy? Good? Okay, I just see a face like, yeah.
So like, with that, so that one we used it once, but the other one we used it twice, like, when we did both. So is that gonna be, why is it, how do we use it twice? Can you straight it?
No, because you're basically looking to see when have you used your data so far? And the way we've used our data is to approximate A naught and A1 when we did our regression analysis. So when we do regression analysis, we have ended up using it twice the data, once to find A naught, once to find A1. So that's why we divide by n minus 2. So if I did a quadratic, what would you divide by? Technically n minus 3. Again, this isn't valid for quadratics. It's only valid for linear, but conceptually, that's kind of what that's saying. Because you have 3 unknowns that you're approximating. Jacob. Because you square these residuals. If you think about the units, let's say yi is temperature. I'm doing some temperature minus some temperature fit squared. Now I'm in Celsius squared or something. Take the square root, now it's in the same units. So once we find the standard error, this is a number. What do we do with this number? Like we have to do our test, right? Yeah, Jacob. That's correct. So if we look at our regression curve, here's our regression curve. What we did was once we find the standard error, we would add to the graph twice the standard error and subtract twice the standard error. This is 95%. This is related to the 95% confidence interval in a way. What we would like to do is count if 95% of the data points fall within those bounds. So if greater than or equal to 95% of points fall within the window, meaning this thing, this area that I'm going to shade in, then we can say it's a good fit or an adequate fit. Yeah, possibly. So basically what this would tell you is like, okay, this fit isn't good. You will have to use some sort of other fit. Maybe I assume my line was just A1x, a line with no y-intercept, for example. The fit was bad based on this test. So maybe I reiterate, or not, I don't want to use the word reiterate. We would start over and say our fit, instead of A1x, is a1x plus a0. So now I give it a y-intercept that's non-zero. Now I redo it. Is it good? It's still not good. Okay, maybe I'll do a quadratic fit. Maybe I'll do an exponential fit or something better. Now note, all these equations don't work for those higher order fits. They only work for linear. But the same idea applies though. Like I want to see what the best fit is to give me that. If this test fails for linear, then it probably should not do linear. Why? It has to do with statistics. That's just like the number that they chose. It has to do with 95% confidence intervals. If you go back to statistics, and I don't know if you've taken that yet, but in statistics, you'll do plus or minus twice the standard deviation a lot of times for 95% confidence intervals for your normal distribution. Same type of thing here. We do plus or minus twice the standard error relative to our regression curve. Questions? Okay. Okay. We didn't talk about the programmatic stuff, so we're not going to worry about that. It's not on the exam because we didn't talk about it. Coefficient of determination. This is the final check. R squared is a metric that compares how far our data points are from the line of best fit. That's SR. And this new thing, how far our data points are from the mean of the data. This is what's called the sum of squares. And what we did is define this metric called the coefficient of determination. This whole thing, R squared, is called that, as the difference between the sum of squares and the sum of the residuals, squared, divided by the sum of squares. And if you were to rewrite it as two separate fractions, you would see this as 1 minus SR over ST. So SR, this is our, yi minus f of xi squared, right? If I want a good fit, what should that be? Yeah, low, close to 0, right? So if this is approximately 0, what is R squared? One. Do you see that? 1 minus 0. R squared is 1. That would mean it's perfect. That's correct. If it's equal to 0, I said approximately 0. So R would be approximately 1. R squared would be approximately 1. This is a good fit. Okay, that's one situation. The other situation is when SR equals ST, which essentially means that the sum of yi minus f of xi squared equals the summation of yi minus y bar squared. What is f of xi? Y bar. So in this situation, that means that our regression line is simply the mean. What does that graph look like? It's a horizontal line. That's correct. So if I were to draw a graph of the data points, if I draw a graph of the data points, let's say I'm trying to get a linear curve from this, whatever, like this. Ideally, our regression model will look something like kind of like this, right? That would be a decent fit, possibly. The worst possible fit you can do is just assume, oh, this is my fit. It's equal to the average of the data points. That's obviously So this is the worst case scenario. What is R squared in that situation? Yeah, 0. Basically, if SR equals ST, if these guys are equal to each other, you get 1 minus 1, you get that R squared is equal to 0. So low R squared is bad. High R squared is good. Between 0 and 1. If you're closer to 1, the better the fit is. Is that okay? And again, I summarize this here. If SR is equal to 0, that means our model fits really well. If SR is equal ST, then that means that SR is equal to the mean. Not a great fit. Doubts? Okay. So we go through this example here, where I basically go through the math of based on the data. I gave you the regression line to start. I gave you that regression line. I told you to find the coefficient of determination. So you first find SR, which are each of the data points, minus the function evaluated at the x values. So this is y1 minus f of x1, squared. Y2 minus f of x2, squared. Y3 minus f of x3, squared. Is that okay? Avi, is that okay? So this is SR. The sum of squares is the same exact type of thing, except we're subtracting the mean of y. So that means we need to find the mean, but just the data points divided by 3, not 2. And some people did that on the exam. You divide by the number of points. You don't divide by 2. I think like 5 people did that on the exam. That's a lot for that. Do not make that mistake. That's a dumb mistake. Dividing this by not the number of terms. So in this example, I give you 3 points. The average is the sum divided by 3. Some people did the sum of that divided by a different number that wasn't 3. So don't make that mistake. That's correct. But people were choosing different numbers for some reason. Don't know why. Be careful, please. So you can calculate it. We get 0.953 in this problem. That's a pretty good fit. That's pretty close to 1. If it was like 0.6, 0.4, 0.2, that obviously is a lot worse. Jacob. I would say no. I don't think there is. It depends on who you ask. I know that sometimes it's not this specific thing, but there's another value in data analysis that's kind of similar that goes between 0 and 1. I know that when we were doing research and doing experimentation, if that value was not 0.999, we would say that it's crap. It depends on the situation. Some people might say 0.95 is good because my data's all over the place. That's a pretty decent fit. Depends. But no, there's no hard standard or anything like that. That's just kind of what it is. Any questions on anything with nonlinear regression? I think that's the entirety of nonlinear regression. It is. So I think we'll take a break now for 10 minutes. Jacob. It can be mathematical, where I say calculate the coefficient of determination, or things like that. I can give you a graph. I can give you 10 data points, and if you count them to see if they fall outside twice, there's I was random ideas. Obviously that's not on the exam. I was thinking about putting that in the exam, but I ended up not. I'll do that maybe in the future. But that's kind of what you can expect. Testing you in if you understand those 3 checks. Okay, let's take a 10-minute break. We'll come back and do integration.